Okay, so we are all set. So any questions with this? At least we all understand the high level idea, right? What symbolic execution is about. And so as you understand, it is a pretty simple but pretty effective technique, because I can like construct any path in the program, collect its path constraint, and then I can solve and try to find out all inputs that could have taken that path. So now let's try to see how we can sort of like enumerate paths in a program very effectively in search for bugs. Okay, so let me just skip this because we are not talking about BMC anyway. Okay, so there are two very popular techniques of doing symbolic execution. The first is what is called concolic execution. I don't know where my this thing is. Okay. Interestingly, I cannot find the. Okay. Right. So, so the first one is what is called concolic execution. The other is what is called EGT, or execution guided execution. I think guided testing. Sorry. Sorry, I'm not used to this tablet so well. So I don't know where I'm writing. Oh, I see. I see the problem. So this is not generated. This is guided testing. So, so what concolic execution does is that it actually starts with a random input. It just randomly selects an input and runs the program with it, concretely runs the program with it. So that will take some path in the program. Once it has done that, it collects, while it is running this particular execution, it also tries to collect the constraints along that path. So whenever there is a branch, like if the branch is true, it adds the branch condition in the symbolic form in the positive form. If the false branch is taken, it puts a negation of that branch, and takes a conjunction of all these branch conditions, and then constructs the concolic, the symbolic path condition. Now, that particular symbolic path condition is guaranteed to take that particular path. So all models of that particular formula will surely always take that particular path. What it does is then it flips one of the branch conditions. Flipping one of the branch conditions would surely ensure it that it will take some other path. And it keeps on doing this flipping till like it runs out of the time budget, or it is able to exhaust all paths. The other option is what is called EGT, or execution guided testing. So what this does is it symbolically executes the program and forks at the branches. So let me just demonstrate EGT with an example. Like for example, think of the program that you just look at the program that you see on the left. And so let us say we have assigned these symbolic names to our variables. A is alpha 0, B is alpha 1, C is alpha 2, and D is alpha 3. What it does is that it starts off with, when it hits the first branch, it actually puts a node in what is called a symbolic execution tree. We'll see this tree very soon. So it puts a node saying that, okay, at this particular line, my path condition is currently true, and I have hit a branch. And because we have hit a branch, there are two possibilities, that I could go left or I could go right. So so the branch could either be false, so A can be less than or equals B, in which case I would take the if part of the branch, and if A is greater than B, we take the else part of the branch. So correspondingly, it gets two different states, and then it tries to explore both the states recursively. So then again, let us say it takes the path where alpha 0. So now you see that because this condition is true, so you can see now that it actually updates this path condition to say that the symbolic value alpha 0 is less than equals symbolic value alpha 1. Then it does the same thing with both the states, it expands them further. Now, if A is less than equals B, in that case, there are two possibilities that it hits upon this particular branch, right? C is greater than D. So correspondingly, it augments this path condition with this new thing. And if C is greater than D, again, it puts the negation of that particular case. And similarly, for the other case where this would have been false, it actually does a fork on this particular branch. So this is called a forking, because like, as you can see, that one state forks into two different states. So this is called forking. So correspondingly, it actually keeps on forking till it exhausts all the paths in the program. So finally, it collects all the path conditions, these whatever you see in the leaf nodes, that alpha 0, the first one is alpha 0 is less than equals alpha 1, and alpha 2 plus 1 is less than equals alpha 3, and so on for each of these leaf nodes. And correspondingly, it solves them and tries to find a model for each of these formula. And then you can find out, so these are the models that it gets, and you know that all models of this particular formula would surely take that particular path, right? For example, if you're looking at path 1, then all models of the path formula would satisfy A is less than equals B and C is less than equals D, which means that they'll all end up hitting this, like they all end up printing high, right? So this is what it is. Any question with this? Any question on EGT? Okay, then if not, then let's look at concurrent testing. In concurrent testing, what we do is that we run the program on a random input. Then we collect the path condition as the program executes. Then we modify the path condition whenever the program terminates. Now, the path condition that you collect, this path condition that you collect when the program executes, this path condition is guaranteed to take the same path that you've already seen. So then what it does is it takes this particular path condition and it modifies this path condition to generate a new input by changing this path condition slightly, right? So like, for example, if your path condition was alpha 0 is less than alpha 1 and alpha 2 is less than alpha 0, then what it could do is that it could, let's say this particular formula is guaranteed to satisfy the path it has already taken. So it can put a negation in front of it. Now it is surely not take that path, but it will take some other path, right? So it keeps on doing that till it exhausts all paths in the program, or it runs out of time. So now what we'll do is that if you've sort of understood this, I'll quickly try to show you a small demo how symbolic execution happens. Since this demo is based on this very popular symbolic execution engine, which has come recently called, not recently, it's been some time that Anger has come. So this is called Anger. And the interesting thing about this particular tool is that it can do symbolic execution on binaries. You don't even need to give it the source code. It actually does, like, it analyzes the binary. It actually decompiles not decompiles, but disassembles the binary, constructs the control flow graph and everything, and then it actually allows you to do symbolic execution on that. So it's a pretty powerful tool. It has become very popular, especially in the security domain. What I've done is I've created a small shell on top of Anger so that I can quickly show you some interesting things through it. So let me just switch my screen to the demo. Sorry, I'm not able to increase the font for. Is it even visible, guys, or do you really need the font to be increased? Or
visible, sir.
Visible,
okay,
sir.
okay. Then let me just stick with it. So okay, so okay, we are in examples already. So there are some examples. Let us see that. So let's start with this very simple program, which was what we tried to do with these equations. So this program is very similar to the apples and bananas problem that we had, right? So it was trying to say that C1 is the cost of apples, C2 is the cost of bananas. So whatever we are scanning, what Anger will do is that it will make them as symbolic inputs, and then it says that 4 times an apple plus 2 times a banana is 50 rupees and so on. and then it actually, so essentially here the at least the program, the way it's structured is that you have to guess the cost of the apple and the banana, right? You have to say what is guess what is the cost of the apple, guess what is the cost of banana, and then given that these two constraints, that if your guess matches this particular thing, then it will say, oh, you guessed it right. That is what it does. And we will see that symbolic execution can solve this, right? So it will actually make them unknown. This is exactly what symbolic execution will do. It will make these two guys unknown, and then it will say that, okay, then because these are unknown, the first constraint will create the first term in the path condition, the second term will create the second term in the path condition, and then it will solve them to find the unknowns, and that is going to be C1 and C2. So let me just compile this program. Okay, so now you are here. So now let's the first thing that we do, let us look at the super graph of this. So that is what Anger would do. What it will do is that like it will create the super graph. So it will say that, okay, what is the super graph of this particular. The problem is that it does not have a, maybe this was not the right program, but it's okay. So we'll see the graph, but I'll show you the super graph also in some other method. So I can say CFG. Okay, so you can see that it has actually disassembled the program, and you could see that there are these different types of edges, right? There is this black edge, which is right. So you can still see because there's printf and all these things. So so there is this, it actually, so there is a call instruction here. So whenever there is a call instruction, it actually calls this particular, so this was like this particular, so this is main, see, this is main, right? So what has happened is that this was a different function. So what it did, so what it did is that it actually called, whenever there is a call, it included the CFG or the control flow graph of that particular function within this particular CFG. So as you can see, there is this particular edge, this black edge. The black edge is basically the call edge. So it has basically said that whenever this call is happening, it moves to this particular basic block, calls this particular basic block, and then this particular edge, this like this gray edge, is basically the return edge. So it is coming out of this particular function back into main. And this dotted gray edge is basically the short circuit path in the control flow graph, right? So if you look at the control flow graph of this particular, of the main function, then you would not see these particular nodes, right? This got included due to constructing the super graph, because we constructed the super graph. So this is the short circuit edge. It basically says that, okay, this is the call that happened, but otherwise we are just moving from this basic block to this particular basic block within that particular function, within main. And then you can see there are these different color nodes. So this is, I think this is a unconditional jump node, unconditional jump edge. Remember, there was unconditional jump, there was conditional jump, and then there was fall through edge, right? So there were these different types of edges, and they are all colored in different colors. Now, what it has done is it actually did this. And now what we can do is that, let me run this program through symbolic execution. And I'll show you the steps slowly, but let us just see if it can solve the problem for us. So when it runs it will take some time. And see, it has said that the guess for a cost of apples. So it created it went through one path which it found it was a wrong guess. It tried to create another path. It found out that it is a wrong guess, but it could find one path where it says it is a correct guess. So can you look at this particular sequence and tell me what really happened? Like if I try to show you the program again. Mission only, right? Equations. Right. So can you look at this program and try to see what really happened? Can somebody explain? It made multiple passes. It gave wrong guess a few times, and then it says then it said correct guess. So it says correct guess, and it says the cost of banana is 10 rupees, and cost of apples is 10 rupees. Cost of banana is 10 rupees. What really happened? Why did it give this output? Okay, so let us try to see how it runs it, right? So how does the engine runs through it? Okay, so you see this address is so let me just fast forward to main. So generally, whenever you have a binary, there are few other things that get called from the glibc library before you even hit main. So let me just call this. Now you are in main, so you will be able to see this. So let us try to see step by step what it did. So currently you are in main, so you can see that this address matches, right? 40076A. This is also 40076A. So you have hit upon this particular basic block now. And what I can do now is I can do a step. So it went to 400630, which is this basic block. So it's basically executing through the program. So now I can again do another step. So 18, this particular basic block. Then 792, this particular basic block. So let me do a couple of more steps. 20. Right. So what we can do is that it will keep on sequentially running these programs. So there is no branching or nothing interesting is happening here. So let me just to save time, let me just fast forward to the place where there is a fork. So we run through some. So it's just running through these different instructions. And it has hit upon a fork where it has forked two states, right? It has forked into 4007E5 and 40081C. So let us check which addresses are these. So you see here 4007E5 and 40081C, right? So now it is at this basic block. And now because there are two edges, right? So this is the I don't know which one is which one, but I think this is the conditional edge, and I think this is the fall through edge. I hope so. But it may be the other way around as well. So now doing that, it has at this point it has actually forked these two children. So it has these two states it is keeping with it, right? So now what it did is that now let us do another step. So it hit upon one more fork, and now it has three pending states. So it made one more run through this particular node in this direction, and this direction there was another fork because there was another. Uh, this particular node also forks into two different branches. So now it has three branches in its states. One is this one. So it is 4007F6 7F, this particular node. Then it has 81C. 81C is this particular node, and 610. 610 is, which one is 610? 610. So it actually progressed along. So remember, it earlier had this one and this one, right? So this guy progressed into this particular node, and this guy came here and actually did a fork. So now we have these three states pending with us: this one, and this one, right? So I can again do a step. So all of them will progress. Again do a step, again do a step, again do a step, do a step. So it actually is progressing through the different steps. And now you see that it has completed some of the states, right? So if we look back, you would see that there is it has 801058. I don't know which one is. If I wait, maybe even be outside this already because it has exited. Maybe it has exited me already. So now if I see completed, the path it has already completed. It has already completed one path where it found out that the guess for the cost of apples is something like, it tried to guess something and it turned out to be a wrong guess, right? And there are two more states pending. So if we step, they will also complete. If we step, this will also complete. And if we now see the completed set of paths, then it says along one path the output was that it was a wrong guess. The other output was it was a wrong guess, and the correct, and one of the paths it's found out it is correct guess, right? So this is how it is running. So can you look at this particular
Sir, it's equations.
oh sorry, yeah. So can you like look at this program and try to now analyze what's going on? So the algorithm is very simple. It keeps on executing things. Whenever there is a branch, it does a fork. It keeps both the true side and the false side with it. And for each of these pending states, it keeps on exploring them further. Eventually, it hits the return or the end exit of the method, and then it gives out whatever output was there to be given. So where did that wrong guess came, and where did it get a correct guess? What really happened? Anybody? So what is going on? Come on, guys, come on. Okay, so let me try to still force an answer. Let me see if I can succeed. So what will happen here when it reaches this particular statement? 4c1 plus 2c2. What will happen when it reaches this statement? What happened when it reached this statement? We saw two forks, right? Remember, I mean, if you look at this particular thing, there are these two, sorry, green red thing you're seeing, right? So one of them is corresponding to this particular branch on this if, right? And the other one, there is again one more branch on this, which corresponds to this particular if, right? And if you um, so so essentially what is this particular path? If you try to see this particular path, what is going on? It says that if this condition becomes true, then come here. If this condition is true, this condition is false, go out. If this condition is false, and then simply go out, right? So essentially that's what it's saying. So if this condition is false, come out. This condition is false, come out. This condition is true, come here. Now can you say what is going on? So you can map it to the program as well. So these two, so this particular check is this check, and this particular check is this check. So what's going on? So anybody can answer back.
So it seems to be taking the false one for the first step and then trying to find an answer.
Right. So how many paths are there in this program?
So the first one being false and then true, and in that case the second one being false and true. So 3, I guess.
Excellent. There are exactly 3 paths, right? Because
Yes.
the first path is where this is false. So it's not doing nothing but enumerating all paths, right? So it will hit upon this particular path. It is false, it comes out and says wrong guess. When this turns out to be true and this becomes false, that is another path. Because this is false, it will come out and say wrong guess. And both of them are true is the third path. On this, it will find out a correct guess and give you the right answer. Excellent. So that is what is happening. So are we all good? Because I'm going to show you some more very interesting examples. And
so how could it determine that C1 and C2? Is it doing a sort of C2 is greater, so we have to reduce that and doing?
No, it is not reducing anything. So it is actually just trying to hit all paths in the program, right? So if you look at this particular program, there are exactly 3 paths, right? One path is where the first guy is like, if you look at this, right? So this is where the control flow is. Everything else is linear, like sequential. There is no other branching in the program. So one path is this path where it is only taking this green edge. The other path is where it's taking the red and then the green. And the third path is where it's taking these 2 red edges. Right? So corresponding to each of these paths, it will create an equation. It will create this path condition. So when it creates the path condition corresponding to the green path, right? This particular green path, that particular guess will turn out to be wrong guess, because that is the path which corresponds to the first guy being false itself, right? So it means the first equation is not satisfied at all. So it will say wrong guess and come out. When this guy comes out to be true, but if the second one is false, comes out to be false, then again it will come out and say wrong guess, because what it means is the first equation is satisfied, but the second equation is not satisfied. And the third path corresponds to the case where both the equations are satisfied. And in this case, it will say correct guess, and and say return and give you because it's exactly solving these two constraints. It will come out and say C1 and C2. This is the answer to C1 C2. Right? Have I answered your question, or do you still see it?
Yes, sir. I got it.
So the only thing is that, as it turned out, there was one path which had the correct guess, and that is all we needed, right? Because it's going to enumerate all paths, it's going to see all paths, and because it's going to see all paths, it will also hit upon the path which had the correct guess, and that is what it's showing out. Any questions? Anybody else? Do we see what is going on? Because I'm going to I switch gears and show you slightly more complicated examples, and as well also because I want to show that, I mean, you can do some crazy things with symbolic execution. Okay, good. So looks like, I think people have hopefully I just take the silence as people have understood it. If not, please let me know, because it's important that we understand it. It's a very simple technique, but a very powerful technique. Okay, so let me exit and see what is the next example we can want to see. I don't know what is branch.c. Okay, not so interesting. Okay, so let us look at this particular program. This is interesting. Let me open it with VI, maybe that will be a little better. Okay, so this is an interesting program. So what it is trying to do is that you have a hidden password, right? So so you have stored, so there is some secret password sitting here, right? Somebody has given a password, like which is sitting here. So what you do is that you decrypt this hidden password, and what the user needs to do. So essentially what is happening is that, see, in the program, the whole program, I have never kept the password in its true form, right? Nobody can look at this program and find out what is the password. Even if I give this file to somebody, they will not be able to figure out this password, because the password is stored in this encrypted format, right? It is stored in this. I have stored this password in an encrypted form. What we do is that we first decrypt this password, and decryption is like, so there is some algorithm to decrypt, so you don't have to worry what it is, but it somehow decrypts password. And then it asks the user that tell me the correct password. So now the user gives the correct password, whatever the right password is. And then it does a comparison and checks if the password matches the decrypted password. If it matches, it says access granted. Otherwise, it says access denied. Right. The cool part is that the password is sort of like I've never even kept the password in its in its unencrypted form. So it's like, even if I share this program to with somebody, they will still not be able to figure out what is the right password, because it's not even stored in in this form. To break this, actually, I'll have to reason through this decryption algorithm, right? And in this case, it's sort of reasonably simple, but in many cases, it may be complex, right? It may not be as simple. So somebody will have to sit, scratch their head, and understand how this decryption is happening if somebody wants to guess the right password. What I'll show is that how quickly can symbolic execution break this. So this is super cool, right? Now, let me load this in. Let me close this particular graph. What was it called? I've already compiled it, so it was called password. Again, I had already compiled it earlier, so we don't have to. And then I need to just to keep the console. Okay, so if I run this, you see the magic. Right. So if you see the output, it says access denied, access denied, access denied, access denied, access denied. But there is one string where it says access granted. And it actually decrypted the password and it said the password is actually nothing but secret. Right. And if I if I run the program with this secret, you would say it will access granted. So I can just to ensure that there is no hanky panky, let me run the program password. Enter password. So if I say secret, it says access granted. So it gets the right password. So see the power of symbolic execution. It was able to reason through the complex decryption algorithm and figure out how to decrypt it and actually come up with the actual password. So again, let me go back to the program. And if you want to see the control flow graph for this, you can. Yeah, so you will see that this is the control flow graph. And incidentally, this also will have some sort of loops, right? Because, yeah, so you can see there is some complex control flow here. There is also some looping because you could see that there were these methods were already using this looping. And now there were more functions. So you can also see this compare function. And so this was the compare function. And this, so you started with mean, then mean called this compare function, then compare. So this is a call edge, mean calls compare, then this is an intra procedural edge within compare. So it goes through this. Then there is a branch in compare. So it goes, one of these edges comes here, the other edges goes there. Then compare is somewhat complicated. It actually goes, it loops and all that. And then so this is a return edge. It comes back to main. And you can see that, so essentially what has happened is I don't know how to make it smaller. Is there a way to make it smaller? Okay, smaller. Yeah, so as you can see that, so this is, you can see that there is I don't know, it's visible, it's very light, but you can see a short circuit edge coming from, so this is mean, right? So this is mean, and there is a short circuit edge coming from here to mean here. So this whole part was compare, right? So this whole part is compare. So it actually included the compares control flow graph within means control flow graph, and that is why it's called a super graph, right? It attaches these control flow graphs together. And then you would actually see decrypt somewhere. It would also call decrypt then. I think decrypt was already called earlier. No, decrypt would happen here. Yeah. So the same thing happened with decrypt. See, this is decrypt. Right? It actually mean would have called decrypt, and yeah, so decrypt. So mean calls decrypt. So this all part was, I think, decrypt's algorithm, and then mean again comes back and calls compare. So yeah, so this is the short circuit edge from mean to mean, and this is the decrypt part. So this is where decrypt is getting called, and then it calls compare, and this whole thing is happening. The cool part is that it is actually reason through decrypt and figure out the correct password. So again, so if I ask you, how did it do it? How was it able to? Yeah. So how was it able to reason on this? So you can stare at this program and try to find out what exactly happened. again, so I mean, see, there is hidden. So when decrypt is called, this hidden is overwritten by the decrypted hidden, right? Whatever is this, it decrypts it and writes back to the same variable, and then it takes a password from the user, compares against it, and if it matches, then it's access granted, otherwise it's access denied. And there is some complicated logic here. Well, not so complicated in this case, but could have been more complicated. But no matter what, symbolic execution was able to reason through it and tell you what is the password. What did it really do? How did it do it? Okay, so before, I mean, we'll come back to this program. Before that, let us try to understand that maybe you will be able to answer it better. But maybe we can look at this particular program first. So this is a very simple program. It's just trying to find out the sum of numbers. And it's every time it's just adding 1, 2, 3, 4 to it, and then it's just returning the sum of the first n numbers or so. So let us load this program. The reason I'm doing that is you'll be able to understand the behavior of symbolic execution on loops. Okay, so let me open the control flow graph. Okay, so this is a control flow graph, and you can see the control flow graph, right? So the main part of the control flow graph is that there is a self loop here. If you see this green edge, this small green edge, right? So it basically comes here, it enters the loop, and then it loops in this procedure for a few times, and then eventually it exits this loop. Right? So now if I run this program, so can somebody tell me how many paths this program has? Okay, so let us see what's going on. So it is currently at this particular basic block. So now if you look at this particular, this is 40076F. I think it is, this must be this particular block. And now it has a decision of going out or coming here. So there are, like you can see that there are two possible states, 40076F, which must be this, and the other one is 81, which is this, or the other way around, right? So let me zoom back in so that I think that we can see the addresses. Yeah, so currently it is at 40076F, 40076F. What is this? Yeah, okay, 40076F. So it is, so this is one pending pending branch, and the other pending branch is 81, this one, right? Because it could come here, so it did a fork. So one of the ends of the fork was this, the other end of fork was this, right? So these two became my pending states. So currently it knows that it has to explore along this and it has to explore along this. So now what it does is that, now see the magic, like, or it is see the fun. So now if I do step, what happened? 40076F, 40076F. Why? Because it expanded on 40076F, and that has one branch coming back to itself, right? So it got into itself again. 4000781, 4000781 was this one, and 40005E0, which is that this guy actually moved forward. Whatever was here, it moved forward. This guy did a fork again, and one of them came back here and one of them went out. You see what happened? So there were these two pending branches, right? This particular branch, this particular state moved ahead. So it came to this particular state now. This particular state did another fork. One of the ends of the fork came back to itself. The other end of the fork went to this particular node. So now we have three pending states. Now if you do a step, you have four pending states. The same thing happened. All of them progressed. This guy did another fork, and one of them came here, the other one came back to itself. 5 states, 6 states, 7 states, 8 states. So what's going on? So when will it end? So this shows one of the weaknesses of, I'll not say weaknesses, but at least one issue with symbolic execution, that when there are loops, it keeps on unrolling the loops. It just says that, okay, what if the loop had taken 1 iteration? What if the loop had taken 2 iterations? What if the loop has taken 3 iterations? And keeps on enumerating all paths corresponding to it. Now, because the number of times the loop is executed is n, right? If you go back to the program, what was it called? I forgot what was the loop. Right. So because this particular the number of times this loop is iterated, this n itself is a symbolic variable, right? So this variable can take just any value. So it doesn't know when to stop. So it assumes that, okay, let n be 1. In that case, okay, the loop should end in 1 iteration. Well, but it is symbolic, so it could have well be 2, it could well be 3, it could well be 4, and it has to go on forever. So this particular program now has infinite paths because it does not know when to stop, because n could be just anything, right? So that is why if you run symbolic execution on this will go on forever. It will never stop. So the number of states keeps on increasing and it will go on forever. Right? So that is why we were saying that symbolic execution is not sound, because it may never be able to reach that particular value of n, which might have shown you the bug. right? So like every other testing strategy, that is why it may not be able to always show you a bug if there exists one. So if we have sort of understood the behavior of symbolic execution and loops, do you want to go back to that program and
So one thing,
tell me?
what happens if user gives negative input? Like, does it consider those cases?
That's a good point. That's a good point. So if you look at this particular program, even you're very right. So when it's actually doing a scan of n, it will also consider negative numbers. It's not that it will only consider positive numbers, right? But then it is actually trying to enumerate not values of n, but it is trying to enumerate the paths. So because see, it's I equals 0 and I is less than n. So for all negative numbers, it is not going to execute any path at all. It will simply come out of the loop, and all of them are in some sense the same equivalence class, right? They will all take the same path. You see what happened?
Yeah, right.
Right, and that is why we were saying that it can actually reason upon. It's a very good question, Akash. Thanks for the question. So because of that, so we remember there were two things we said. One thing we said is that okay, it is symbolic execution is not sound because it may not be able to show you a bug if there exists one. But at the same time, symbolic execution can reason on infinite set of inputs. So what happened here is that there is this one path which does not even enter the loop, right? Where values of n can be n are negative. So, but how many negative numbers are there? Is an infinite number of negative numbers, right? And if this particular path where n was negative and it came out of the loop, right? The loop was not even entered. So all the negative numbers would take that path. And if that path does not have a bug, we know that for this infinite set of inputs, right, all these negative numbers, we know that no negative number can give you a bug. So symbolic execution, it is able to talk about an infinite set of inputs because every path, there can be an infinite set of inputs taking that path. And if that path does not have an error, that you know that like nothing can, like no matter what happens, that infinite set of inputs, like no input in that infinite set can ever give an error. So that is the power of symbolic execution. So it is not looking at testing some concrete values, but it is saying that, okay, every possible set of values which satisfy this formula, right, cannot have an error. And the number of models of that particular formula can be infinite. I mean, there can be infinite set of inputs that could have taken that path. So it's a very good question. Excellent question. Thanks for that question. And so yeah, so though it is, so for all negative numbers, because it's just enumerating paths, it's not trying to enumerate values of n, it is enumerating paths. All paths take the same paths, and it knows for that path that none of the negative numbers can give a bug, right? So that is true. Great question. Yeah, any other question on this? So now let me go back to the previous thing. Let me just see if we can now reason, because we understand loops a little better. Let us see if we can understand this particular program, because this is a pretty cool program that it can. Yeah. So this is a pretty cool program that it could actually reason on such complicated things. So can we now try to understand what's going on? How did it really figure this out? So, okay. So let me just, in the interest of time, tell you quickly what is going on. But you guys still have to like wrap your head around it and maybe think back and see that you really completely understand it. So what it is doing is that, so the first problem is not there, because first problem in the sense that does it have infinite paths? It does not have infinite paths, because like if you see any of these loops, they are all bounded, because it says that string length of password, the password being passed to it is a finite length string, right? So this particular loop can only go a finite number of times, right? And the same is the case with this loop, because it's comparing strings. Whenever any of the strings ends, it will come out, right? Or I think both the strings. I have to see the logic, but it doesn't matter. We are only looking at finite size strings, so none of these two loops will go on forever. So the program has a finite number of paths. That much we know now. The other next thing to know is that what will it do? It will enumerate all paths in the program, right? And what are the different paths in the program? The different paths in the program are these for loops unrolled a different number of times, right? So this for loop unrolled 1 time, 2 times, 3 times, so on. Similarly, this for loop unrolled 1 time, 2 times, 3 times, 4 times, and so on. Now, one thing to remember is that there surely exists one path. So now look at this particular decrypt routine, right? So this routine there is nothing symbolic about it, right? So this hidden is a concrete string, right? So when you do a decrypt, it actually walking through a concrete string and doing some transformation. So this transformation is completely deterministic. In fact, if I could put a print, I could actually print what this guy is. So it doesn't matter what the input is, because the input is even coming here. Even before that, this hidden is doing something like this. So now the compare is that the only thing that is sort of, there is something symbolic is in this compare, because here, so this enter password, the password coming from the user is symbolic, right? So the compare routine is comparing a symbolic string, a string where an unknown string which is coming from the user, it is comparing it against the a known string which is this hidden, which is this decrypted password, right? And it is going to unroll this particular compare. So it's going to unroll it 1 time, 2 times, 3 times, 4 times. So what do they correspond? The like unrolling it 1 time means that it means that none of the characters met. Like none of the, like even the two strings, that is the hidden string and the string that came from the user, they do not match even on the first character. Unrolling twice means they match only on the first character. Thrice means it only matches on the first two characters, and so on, right? So there will be one path in that which will, where these two strings will match for all the characters, right? Whatever is that string, where it matches for all the correct characters, that is where this compare will succeed. Like this compare will come and it will hit and it will say that access correct. So because it's enumerating all paths, there does exist one path where all the characters would meet, right, would match up. And on that, this will take this particular if, and it will say access granted. So it's only a matter of looking at all the paths that it has enumerated and finding out which path was successful in decrypting it. Where this unrolled it as many times, it was required to and say that all the paths met, right? All the characters in these two strings met. Remember, I mean, I'm saying that, okay, the character coming from the user, but understand that this is a symbolic string, right? So it's creating an equation and saying on that equation, all the characters in these two strings are equal, right? So it is saying, so I don't know how to say it well, but it's saying that hidden's 0 character is equal to the symbolic string's first 0th character. Hidden's 1 character is equal to the symbolic strings of the one character of the symbolic string, and so on. And then it will ask the theorem prover to give it a satisfying assignment. And of course, it will say all of them are equal, so it must be equal to the decrypted string, and that is where the access is getting done. Yeah, I don't know if I did a good job of explaining it, but all I wanted to illustrate is that you can do some really cool, crazy things with symbolic execution.
Sir, is it
Yeah.
doing like something like this? It is first checking character A, as it is, as a password is secret. It is first checking character A and it is not met, and then B, and then after it comes with S, and then it again checking the character with A, B, and C, and then it comes with E, and two characters met, and that's why again it spread the branches. Is it working like this?
Not exactly that way, but okay. Let me do this. Let me go back to the control flow graph of this particular. Okay, so So this is the decrypt routine, and as I said, decrypt routine is completely deterministic. There is nothing symbolic about it. So we don't have to even worry about it. What is interesting is happening is in the compare routine, right? So in the compare routine, you have this loop, which this is this loop, and you can see that this loop is, so this loop you can see, right? So this red arrow, which is this loop, right? So it is going through this loop. So remember the way we saw how symbolic execution works on the loop? It actually unrolls it a different number of times every time, right? So first time it will come unroll it once, unroll it twice, and so on. So each unroll is a path. So what does it mean? So it means that it can take this path, which is comes like red arrow, red arrow, red arrow, green arrow, green arrow. So that means it just runs through the loop only once, right? It can even not even enter the loop. So it can just from here, it can take the green arrow, completely avoid the loop, or it can take the loop once, or it can take red arrow, red arrow, red arrow, green arrow, red arrow, red arrow, green arrow, again come out of the loop, right? So it means that what happened is that the compare, so so it will enumerate, so symbolic execution will blindly enumerate all paths, right? So eventually there will be one path which actually keeps on going through the string for across all the characters in the string, right? And that particular path will be the path where it will get the decrypted string, right? So it's blindly enumerating all paths. It's not doing anything more than that. It is not doing anything more clever than that. It's brute force enumerating all paths. And as it happens, there is one path where it will keep on matching all characters, right? That is surely one path, right? One path is that it will match only on the first character. The other path is it will match the first two characters. Other, it will match the first three characters but not match the next character, right? So whenever it doesn't match a character, compare returns, right? So the one path is it does not match any character, so it returns the very first time. It does not even enter the loop. Then it matches the first character, right? So it runs through the loop once. It matches the first character but does not match the second character. Matches the first two characters, does not match the third character, and so on. So there would be one path which will match all the characters, and that is the path that we are looking for, right? And because it's enumerating all paths, it will enumerate that path also, and because it enumerated that path, that will satisfy it. So that is all that is happening, but nothing more than that. But when you run it, it looks like magic. So that is something.
Yes, sir. Thank you. I got it.
Sure.
But sir, it is not for this problem, but it is made possible that as it running in the brute force, it may come to running in exponential complexity. Is it not? Means as it running in brute force, so every path is considering. So it may possible to come in an exponential complexity.
It's not even exponential. It is undecidable, right? Because we saw that there are paths there are infinite number of paths, so it may not even end, right?
Yes. Okay.
So yeah, so it's not even that it's guaranteed to even terminate. So it may never halt at all.
Oh,
Right? So
okay. I got it. Thank you, sir.
sure. Great. So let's come back to the slides. I hope you have got some good idea of how symbolic execution works. Okay. So you've got some idea of how symbolic execution works. So in real world, there are more problems with symbolic execution. Overall, the idea looks pretty cool and pretty simple. But in real world, you have like external function calls, you have vector instructions, you have system calls, you have floating point instructions, nonlinear arithmetic. There are many difficult things that are difficult to reason for symbolic execution. So there are two very powerful techniques that symbolic execution uses to combat these problems. One is called concretization, the other is called virtualization. So concretization is that, think about this particular function where there is a function which is, let's say, foo, and foo is basically an external function. So you can understand that you would need the some sort of code for your, something like anger is able to do things on binaries, but then in most symbolic execution engines you actually need the source code. And think about it. I mean, so now the thing is that, so if the, let's say, if you do not, or even other things, like for example, this thing was one problem. There could be other things which are difficult to reason on, like for example, there are like vector instructions, right? Reasoning on that and creating a formula on vector instructions could be hard. Floating point instructions, that could be hard. If you have nonlinear reasoning, nonlinear arithmetic, again, even if you create the formula, your symbolic execution engines may not be able to solve it. So now the problem is that if, let's say, there is this hard to analyze function foo that you do not know how to handle, and you get that in symbolic execution. So what can you do? So here symbolic execution uses a very cool trick. So okay, so now, like, if you have such a function, there are two possibilities that you could do, right? You can do an over approximation. You can say that, okay, there is foo that I cannot reason on. I do not know what can foo return. So let me assume that foo can return everything, right? So you say that foo is equal to y is equal to star. Star means it can just return any possible value. That is one possibility, and that is very safe, right? Because whatever value foo returns, that can only be a subset of the values of all possible values, right? So we are not missing out on any value. The problem of this over approximation is that your path will blow up, and you will get a lot of what are called false positives, that you will get bugs. The symbolic execution engine will return bugs, but those bugs do not even exist because the path is infeasible. I mean, that value cannot even occur. The other option is to do an under approximation, that is what is called concretization. You can actually find out a value that foo can return, a single value that foo can return, and put y equal to that value. So so this is what concretization does. It basically says that, okay, whenever you hit upon a function that is hard to analyze, that symbolic execution cannot analyze, what symbolic execution does is that it actually finds out the symbolic expression of this x, whatever is symbolic expression of this x, and for this parameter, it tries to solve that parameter and try to find a feasible value, which is a possible value that this particular foo can run with. It actually concretely executes function foo on that particular value, and whatever is the output, that it assigns to y. Right? And then it continues. So now y is no more symbolic. Y is a concrete value, as we call it. It's a one constant value. We call it a concrete value. And then the rest of the execution happens with that particular value. So this is something called concretization. And it has been one of the very powerful techniques of using symbolic execution for real world programs. Of course, the problem is that it further reduces soundness because we are missing out on a lot of values, right? So instead of pulling out all possible values that foo can return, we are picking only one value from that set and running with it. So, but it was anyway hard to analyze. So there was nothing much we could have done. The other thing is, like, other difficulty running these programs is modeling heap memory. So so whenever you have mallocs in your program, so what do? So generally what it does is that one possible way of handling these problems is that you can use a special array or a special variable to modify, to express as a heap. So you say h of a is all the locations that malloc models, right, or malloc has returned. You summarize the whole thing with one particular variable, and then you and then you replace all your I mean, so whenever you are writing, like, if you do like ax equals 5, you say you are writing to ha, and when you say that, like, you are doing something, you're clearing something, you say, like, let's just set ha to 0. So like these elements of ha. So you can think of, the way to think about it is, you can model this heap, this whatever this malloc has returned, you can model the whole thing as an array, as a large array, and then there are segments of memory, like there are fragments of so there are decision procedures in SMT to model arrays, right? So there is this array theory which is available, and you can use the array theory to model. So there are some axioms that you have in the array theory, and you can use those axioms to model model the heap. So you just model the heap as an array, and then you say that, let me just try to use the array theory to model the rest of the heap. Then there is something called virtualization. So virtualization means that, like, for example, if you have system calls that you cannot analyze, again, so because system calls are going into the operating system, so your symbolic execution is only looking at the program that you're trying to run. So it might be difficult for symbolic execution to handle those cases. And so there have been symbolic execution engines which have been built to even run things through the operating system. So it uses something called virtualization. So essentially you can run the execution in a virtualized environment, like something, maybe something like Kemu, and then you can do symbolic execution on the whole virtual environment. So you can think of the whole virtual environment as one program, including the operating system, and you can drive symbolic execution through the whole system. So it's doing symbolic execution at a very large scale, but people have done it. So there is this very cool tool called S2E, which is able to do such things. Now coming back to the applications of symbolic execution, there are many applications of symbolic execution. Of course, one is test case generation that we have already seen, because it's able to solve the path conditions at the end and generate test cases. People have also used symbolic execution for something called program debugging. So like, for example, you have a program and you do not know what the bug in the program is. People have like used some techniques on symbolic execution to say what might be the problem. People have tried to use symbolic execution for automated program repair. That is, they say that, okay, can I have a, okay, so you have a program which is not correct, and I want to come up with an automatic synthesizer patch. When you apply that patch to that program, that program now becomes correct. And there have been techniques based on symbolic execution. In fact, even our group has some work on this automated repair. Then we have been able to, I mean, there is some work on bucketing tests. Like, for example, you want to find out which tests are similar. So that because you would like to assign developers to similar errors rather than giving every bug you want to assign to different developers. So there is some work on bucketing tests, some work on automated debugging, and also program synthesis. Again, this is, in fact, this is a paper by Avnish. So you can even use symbolic execution for even automatically creating programs. So with that, I'll end my talk. So there were some more things we could have talked of, but let me defer it. Any questions?
Hello.
Yes, Adam.
Yeah, first of all, why are there two categories, program debugging and debugging? Do they like represent?
I should have merged them. Sorry. Yeah, I think I kept on increasing my slides and. So,
Okay.
By the way, this debugging, I wanted to say like interactive debugging. So actually, both the papers are from our group, and so here what we do is that we do symbolic execution on. So I would rather say this is interactive debugging. Let me. So essentially, what we do is like for example, what you have a, let's say you already found out that there is a bug in a program, right? So you want to find out that what must be the reason for that bug, or how do I fix that bug? And what these tools allow you to do is that you can actually be, so you take that particular path on which there was this bug, and you do a symbolic execution on that path, right? Because you have done symbolic execution on that path, you have much more understanding. So you have this path condition, which now has much more information about that path. And then you try to say that, okay, how can I change this particular path so that, or the instructions on that path, so that that bug is no more seen, right? You are only trying to fix that path. So you do a symbolic execution on that path and try to find out how, like, what could be wrong in that path. So that is what, and it does things in an interactive environment, right? So the user can say, okay, go here, go there. So that is
All right. And I had another question.
sure.
Regarding concolic execution, so like about like what we were talking about flipping, so we would not like flip the entire path constraint, right?
No. So people generally, the one very disciplined way of doing is doing some sort of a depth first search. So what people do is that I did not talk about it, but let me just try to say what I mean. So like for example, you have a path condition, say C1, uh, C2, C3, C4. So the way people do this is that, at least one of the ways to do this is to say that, okay, let's say the first path gave me this particular path condition, right? So now what it does is they do is they go and flip the last path, the last predicate on that path. So now in terms of the control flow graph, if you think about it, let me try to draw the control flow graph. So yeah, so the way it would work is that, let us say, this was C1, then you got C2, then you got C3, then you got C4, right? So this, let's say, happened. Now you decided that you just flip the last one and you make it not C4. So now not C4 means what? It basically, instead of taking this branch, rather this side of the branch, it actually takes this side of the branch, right? So now you will take this particular path, right? You will take the path which is this path. So now once you have done that, so then you say, okay, I have seen both C4 and not of C4 with this context. So now just let me just drop this guy completely and now take this guy and do a not of C3. So that is the next path that you generate. So then you say that, okay, C3. So when you say not of C3, then what will happen is that it will take the other side of the previous branch. So it will do this. And then similarly, it will explore all the whole tree under this. And then again, it will say, okay, now I have seen the whole of C3. Now let me just do a not of C2. So not of C2 means it will come here, right? Again, it will use the same procedure and explore this whole tree under it, right? And eventually it will say, okay, let me do a not of C1. So when it does not of C1, it will again take this branch and cover the whole thing under it. So in some sense, you think of this is some sort of a depth first search, right? So you are looking at this, then you're looking at this, then you going up one further, again going there, again you are doing full traversal on this part of the tree. And so this is one way of exploring things using concurrent execution. Of course, I mean, you can use other strategies as well, but this is a very, very common strategy, a very popular strategy, let me say.
All right, thanks. And like this is somewhat of a practical question, but like I have like some experience with Z3 and no, sorry, Clee, sorry, right, with Clee, and like in my experience, Clee wasn't like able to, let's say, analyze even a very small program with like a very bounded loop. Like that was just my experience. So like I wanted to ask, like is it like have you seen it like being used like practically for good code bases?
I mean, we have used Clee. I mean, we have been using Clee for quite some time. In fact, we have built other tools on top of Clee. In fact, many of these tools are built on top of Clee that I was talking here, and like, and it works. I mean, we have found it to be very, very powerful. So you have to tell me, if you show me the program on which it did not work, I can tell you why it did not work on that. And that is why it requires you to have some understanding of what symbolic execution can do and what it cannot do. So if you apply it in the right way, it surely works well. But of course, it has its own problems. So in fact, I mean, one of the problems is we have improved Clee for, in some respect, like, so we have this paper called deferred concretization. You can look at this paper as well. So this actually tries to find out, so it tries to overcome some of the weaknesses in Clee, and it uses fuzzing to do that. It actually combines Clee and fuzzing, and so this actually handles these concretization problems. So when Clee concretizes, it actually like creates some problems. I mean, if you look at the paper, it will tell you that. And this particular paper actually tries to handle some of these things. But other than that, I mean, we have found Clee to be very effective on even very, very large code bases. And many of the tools have been mentioned here. Many of these are our papers, and many of these papers are, are built on top of Clee. So it must be that you have used some very complicated example. I mean, maybe there was something which Clee could not reason on. Maybe there was some some very complicated formula that you might have used, like
Practically it was just like passing a 9-digit number like from a string into a number. But like I have the program, I'll share it and like
oh
then
yeah,
we
yeah,
can
sure,
discuss it.
sure. I can take a look. So there must be something in that which Klee found out very difficult to use, and often there are tricks. Like there are like it's sort of a black art as well, because you have to know how to use these tools well. So sometimes you can change the program even very slightly, and then you would see that the result magically changes. I mean, the tool is able to do much better, much better. So that is why it's important to understand the theory also, because then that tells you that okay, what it may not be able to do, what where it must be struggling, and you can maybe help it out a little bit there.
Sorry, one question. So
Sure.
Clee was not halting, or you are not getting the bug.
So what happened was that like we ran for like 5 hours, and after that I'm not sure whether it like would have halted or it would have given an error, because like I had to stop it then.
Okay.
So, so Klee usually generates, I mean, like the way Sir was showing in the demo, Klee actually generates like test cases for each path. So, like, could Klee generate something like in the Klee out folder, or like, could you like share that as well? Like, we can see what values it is generating or what.
Yes, and I mean, you can even share the program with us. I mean, both like all. I mean, Sumit, Avnish, they are all experts on Klee, so they can tell you very quickly what must be the problem.
Yeah, sure, I'll do that, because like that's something that's been like niggling at me for some time. So yeah,
Oh, sure. Even I'll be curious. I mean, we'll be curious as to what must be the program. And thank you guys. So it was a nice session. Thank you guys for the questions.